Let us now see inclined planes, but now when we have three bodies, the double inclined planes you've been seeing, we are having two bodies. Now we have here three bodies. Okay, the diagram below shows a 12 kilogram mass on a rough horizontal plane. The 6 kilogram and the 4 kilogram masses are on rough planes inclined at 60 and 30 degrees respectively, meaning the 60 goes with this 6 and then the 4 goes with the one which is 30. The masses are connected by two light inextensible strings passing over smooth fixed pulleys at A and B as shown in the diagram below. If the planes are equally rough, now there means that they have the same coefficient of friction. If you hear the word equally rough, it means that mu is the same on those two or three planes. With the coefficient of friction 12, and the system is released from rest, find the acceleration of the system, then the tension in the springs. Okay, we have two springs, so we have different tensions, and we have three different masses. It means that they are having different reactions. So let us start by getting their weights. So the weight here is going to be, we get this times B, then it's going to be having resultant. This one is also having resultant, but its weight is vertical C, 6 times B. So let us call this one resultant 1. So this one will be resultant 2. And then this will be having resultant 3. The resultant is always perpendicular to the plane. So this one is going to be having a weight of 4 times G. After putting the weights at the resultants, it means that we put now resolve those weights. This one is okay. So resolve this weight into a vertical to the, a force perpendicular and then power to the plane. So this will be now 6G cos 60 degrees, because this is going to be 60 degrees. Then this one is going to be 6G sine 60 degrees. Then, if you have to resolve this one, you are going to be having 4G sine 30 degrees. Then this one, you are going to be having 4G cos 30 degrees. That is the basic start with resolving the forces. Now, we know that we are going to be having the tension in here. Let us call it T1 in this string. This is the same string. Even here, T1, T1. But here the string is different, so different tension also. Let us call it T2, T2, the same here, T2, T2. Okay, after putting in the tension, now our focus comes to the acceleration. So we are done with almost. So our acceleration, which one is bigger? So meaning if this is bigger, our acceleration is going to be pulled in this direction. So that our acceleration is going to be in this direction, meaning this one it will be in that direction. Then this one it will be pulled up in that direction. So because this one we expect it to be like this, so that's where the acceleration is going to be moving. If the acceleration is moving, then friction is going to be opposite. So if this one is moving down, then friction is going to be opposite. So we say mu is the same, but it depends on the resultant here, which is R1. So this one is being pushed in this direction. So acceleration will be backwards. So mu, then the resultant of that weight. Because the resultant depending on the weight is going to be different. Then this one is pushed there. Then our frictional force is going to act opposite it, which will be mu, then R3. When you done this, remember if the acceleration is in one direction, then friction is going to be in the same direction also, opposite to that. But you see the friction, I think we see this R, this R, this R. When you look at acceleration, this R, and then there's that arrow. The same, but friction is acting opposite to them. So after doing that, I think basically we are done. We just get into our questions here. Hey, so now we start with now the 6 kilogram mass. They gave us our mu as minus 1 over 12. Let us start with the 6 kilogram mass. If you read, we started by resolving in that direction. Remember, there is no acceleration in this direction, so it means that this force is balancing with that. So our R1, I mean, this equation is start by getting this resultant. So our R1, which will be 6 into 9.8 cos 60 is a half. So our R1 is going to be 29.4 newtons. So I'm done with this. So after that, then I come to this particle. This acceleration is in this direction. That's where the acceleration is in that direction. So our resultant force should be equal to ma. So the resultant is pushing it in this direction. We have 6e, then sine 60 degrees, then minus. We have T1 which is opposing. So T1 is opposing. This T1 is opposing. Then also friction. Then minus mu R1 be equal to the mass, which is 6 times the acceleration we don't know. So from here we can every substitute. This is going to be 6 into 9.8 root 3 over 2, then minus T1 minus mu, they told us it's 1 over 12 into our R1. Our R1 is 29.4 equaling 6a. So if I make T 1 and I push everything the other side, my T1 is going to be, so if I simplify this, this will be now 3 times be 6a minus 48.4723. So I call this equation 1. Now, when I come now to let us consider the 4 kilogram mass by 4 kilogram mass, if I consider it, this one is that. First of all, I resolve the forces which are perpendicular to the plane. This, so I have my R3 equaling 2, so it's going to be equaling 4d, then cos 30 degrees. And from here, my R3 will be 4 into 9.8, then root 3 over 2, because cos 30 is that. So my R3 will be equaling to, this is going to be 1.96 root 3 newtons. I don't want out of the small points. Okay, so now we come to now our acceleration. So that our acceleration is in this direction here, like that. So this is where our acceleration is b, equaling to ma. So now, so what is pushing us? Always, this direction of the acceleration is very important. So see that we are being pushed in that direction by this force, T2. Then there are those opposing. The first one is this one, 4d, sine 30 degrees. Then of course, minus the friction, mu, R3, equaling to the force, the mass, which is then times the acceleration. Remember, acceleration is going to be the same. Okay, so from here, I have my minus 4 into 9.8 sine 30 is a half minus 1 over 12 into 9.6 root 3 equaling to 4a. From there, I can aggregate my T2 as, okay, I'm going to start with this. So it's going to be 4A plus 22.4290 if we take it their side. Okay, so now when you come to now our 12 kilogram mass, what do we have there? Start there. We first get its resultant in this direction. Our R2 is going to be 12G. Our R2 here is going to be, which will be 12 into 9.8. So which will be this, then times that. So which will be 117.6 newtons. So I have the resultant there. Now, if I come the acceleration, start my acceleration on that particle, it's going to be in that direction. So what is pushing us in that direction is a certain force. So we get a resultant. First of all, in this direction, we are being pushed by T1, then minus T2, then minus, of course, the friction, mu R2 equal to the mass 12 times the acceleration. So, you know that we have everything. We have this, we have that. So, if we put in that equation, so we put this T2, we put also this at once. So, my T1 here, okay, my T1 here is going to be 6A minus 48.4723. Okay? Then minus T2. My T2 from there is 4A plus 22.4290. Then minus mu, which is 1 over 12 into R2, which is 117.6. Equaling to now 12A. This A I'm looking for. So from there, you see, this is going to give me, okay, let us just simplify and see what it shall be with at the end. So, from here I start with this. Okay, then so here I'm getting 18 when I combine, when I combine these forces and I take them the other side, or if I have here, I'll be having this minus, so this 6 minus this, I get 2A, this minus this, then minus 80.7013, all equal to 12A. So sum. Okay, simplifying there. So in our T1 there, I think you see. But wait a little bit. This T1, when you take this T1 inside, it becomes positive. So, oh, sorry. This one, it was negative. This was negative, and this was supposed to be positive. Yeah. When we take this side, this one remains positive, then we bring this one becomes negative. So, I think here we are going to redo this one here. Sorry. So this one is giving us our T1, which was negative 6. Yeah, negative 6A. Then plus 8.4723. Yeah, so substituting this value now here, and then we simplify. So this one I'll be having minus, I'll be having negative 10A. Then we get this one, we simplify here. This one is going to be now a plus. This one is going to give me 48.4723 minus So here I'm getting 26.8, sorry. Then minus the other one. Minus this. So here I'm getting 16.2433. When you get this, minus this, then minus this, equaling to 12a. So from there, you can every so when I take this side, I get 22a equaling 16.2433. And so from here, I can see that my expression is going to be 0.7383 meters per second squared. So that's going to be my acceleration. So now, after getting the acceleration of the system, now we want me to pay the tensions in the spring. What is the first spring? First of all, we have this, then we have this. So, part B, tension is in the spring, so my T1 is going to be from equation 1. From equation 1 here I have negative 6 into 0.7383, then plus 48.4723. Then our T2 will be from there. We have 4 into 0.7383, then plus 22.429. So from there, our T2 is going to be give 4 decimal places. Even here, our T1 to 4 decimal places. Okay, when I press this, I have 7, 3, 8, 3 plus 4. So here I'm getting 44.0425, and these are returns. When it comes to this, we have 4. So here I'm getting 25.3822 units. And that would be our answer. So that's how you handle this diagram there. You have to be careful, like when you take this side becomes positive, when you bring this side becomes negative, when you simplify this and this together. That. So here you have to be very, very careful. Now, some people tend to round off to less than 2 decimal places. There will be, we call it premature or premature approximation, and the rules actually say max. So that's it. I wish you well.